what we wanted to say was that frequency distributions tell us how many people are at a certain point. So there are some people that don't drive at all, or maybe shouldn't drive at all, like my grandfather. But a little dark, he died a couple years ago. Still, when he was still driving, he should not have been driving, right? So we're hoping that Pepe's over here. And there are some people, like my friend Michelle, who drives way too much for work, and she's out here. But a majority of us land somewhere here. I don't know. How many miles do you drive in a year? I think, this is me making it up. I'm pulling my in-law here. I think it's 10,000? I'll make that up. Right? The average amount of miles per year. I'm sure the insurance company knows that. And so it could look like something like this. And this is called, what we're going to say is a unimodal. Unimodal meaning one. Uni means one. And then modal, for now, we can call that a peak. There's one peak in this, and it is symmetric, which means that each side looks about the same. You can flip them over and they look identical. So we break this down the middle. This half looks just like, you could flip it and it would be the same on that half. So these are called unimodal symmetric distributions. Here, this also looks like it could be symmetric because we could divide it in half out here and again flip it. But there's a difference between this one and the one over there. What is the difference between top left and top right? Yeah, 2 peaks. 2 peaks. So not unimodal, but bimodal, right? Bi for 2, bimodal. Peaks, and it's symmetric. So it's symmetric, bimodal. We then usually in psych talk about these two. And so they have a quality of top left where they have one peak. Right? We have a peak here and a peak here. The difference is they're no longer symmetric, right? You can't really flip this in half and get the same graph from the peak. And so we call them skewed. And we define the difference between them by saying which way do they point? Like which way is that tail pointing? You can imagine if this is our graph, this is kind of like the y-axis of the graph. So this is 0, this is some big number, and this is, if we kept going, this would be some negative number. And so since this tail, since the graph is sloping down towards the negatives, we call it a negative skew. Negative skewed, unimodal. Yeah.
Are these explanations going to be on videos?
Yes.
As well? Okay.
Yeah.
So you're explaining the same things.
I am.
Okay.
Just a little bit, because I like brushed through, I felt, and I wasn't really expecting having to watch 4 videos before class even began. Granted, it's a little bit. Do it less of like a review. I'm more going to be adding material on as the semester goes on, but like for now, yeah, quick review and stuff.
Would it also be okay if we called it like positive and left skew, or I'm so sorry, right and left skew instead of positive and negative, or do you prefer like that?
That is fine. Yeah, you can say left or right.
Okay.
So if you're going to go with that term, is this a left skew or a right skew?
That would be a left skew.
Left skew, right? Because it's pointing to the left. So you can also say negative, or you can say left. Right. So if this is left skew, then this one would be
Right, positive.
right or positive skew, right? Yeah. Positive or right. One more thing on that, actually, I was thinking about this. I think they are on Canvas in the modules, but Panopto has a way for me to upload slides. Again, I've never used Panopto, so I did that. I don't know if that's easily accessible to you. But you should know that the slides should be connected to the videos on and off, so you should be able to access like what I'm using in the slide, you should be able to download it. And if you can't, let me know. But they're also on Canvas, because I was scared that you wouldn't be able to. And then this is the last one. And so we were talking about how the data that the researchers were using was about car mileage, right? How many miles do you drive a year? And this is what their data had looked like. And so what this meant was that, there were 350 people that drove no miles, and there was 350 people that drove a ton of miles, and 350 people that drove a medium amount of miles, and pretty much everyone drove the same amount of miles. Sorry, slacking on this. This would be similar to like rolling a die. If a die is fair, then you're likely to roll each side of the die an equal number of times. Right. 1 out of 6 times is going to be a 1. 1 out of 6 times will be a 2, a 3, a 4, a 5. And so we call this uniform. Uniform. It's the uniform distribution. We don't see it a lot in psychology because people tend to vary, right? Like, it's not the case that there's an equal chance we all get something. Some people are going to do something more than other people. So uniform distributions don't show up a lot. But we can think of like a great example would be rolling a die. Or things like flipping a coin. How many times is it going to, like, what is the proportion? It'll be heads. What is the proportion? Will be tails. It's going to be 50-50. They'll be the same amount. And so what we did is we looked at this, and because they just plotted the data, they were like, this must be fake. Because there's no way that driving a car is a uniform distribution. We'd much more likely expect either like a positive or right skew, or even a unimodal symmetric, or like it's just like the distribution of what we would imagine car mileage is in a year is not uniform. And so understanding just kind of distributions and how we graph them was kind of the first day's videos. I'm talking about frequencies, how do we construct a frequency table. And so we're going to kind of start class by working on that. But before, I wanted to highlight one more thing about why stats is like crazy and interesting, and why I think it is important is, one, everyone lies, right? And so here I just kind of grabbed headlines of various big famous professors who have been caught lying and faking their data. For us, like the most relevant is Francesca Ginu, because she's from Harvard. And people have definitely talked about the fact that she is a woman and she's getting a lot more like publicity on her fraud versus her co-author, Dan Ariely. He's at Duke, I think, and no one is really talking about his scandal, right? Like, it's not the best. But they both study dishonesty and they fake their data about honesty. Regardless, right, it happens a lot. So like that car example is not the only example. This happens all the time for a lot of reasons. And the one that I really enjoy, and for me, it says this is why we use Jamovi in this class, happened, at this point is probably 10 years ago.
In bad times, you have to slash government spending. Now, I don't need some fancy Ivy League paper to tell me that, because there's already a fancy Ivy League paper to tell me that. The famous 2010 study, Growth in a Time of Debt, by Harvard economists Ken Rogoff and Carmen Reinhart. Independent economists have found that debt loads greater than 90% of GDP could result in the loss of up to 1 million jobs. A grad student, Thomas Herndon, a 28-year-old University of Massachusetts Amherst, had an assignment: rerun someone else's data and see if you can get the same results. Herndon chose the Reinhart-Rogoff study. First thing he sees is the crucial column in their data, the one that averages the growth rates of countries with debt to GDP ratios 90%, is wrong. If you correct the spreadsheet error and put the intentionally omitted countries back into the data set, instead of countries with the dangerous level of 90% debt to GDP having a negative growth rate of 0.1%, they have a modestly positive growth rate of 2.2%. That is a big freaking difference. That's the difference between recession and recovery. But come on, 2.2% up, 0.1% down. You say potato, I say eliminate food stamps. But folks, Siegfried and Roy are standing by their results, saying, quote, the weight of the evidence to date, including this latest comment by Herndon, seems entirely consistent with our original interpretation of the data. Right, entirely consistent with their interpretation, because no matter how much the results change, the hypothesis must remain the same. That's science.
So basically, it was a big scandal because this paper was every like major country in the world was talking about it and showing. They basically showed that like the more you spend when times are tough, the worse the outcomes are. And the best thing to do when times are tough is to like lay off people, fire them, and then things will get better. And governments were talking about this. There was multiple hearings in Congress about it. People were changing economic policies based on this paper. And so this grad student comes along and he opens the data set, and they had used Excel. So it's one of those like, you have the formula and it's like from A1 to A75, and you can like kind of select things. They were doing it by hand and they didn't select all the way down their column. They like made a typo and it only selected some of the data. Even though they had more data to analyze, it just left some off. And so when you fix it and don't do it by hand, but use software to do it, it totally changed the results. And what I really emphasize is that people were using stuff like Excel to type in their little functions to try to calculate and do all the statistics for them, and they were making mistakes. And if we just trusted the software to do the calculations for us, there would be less mistakes. Right? And so this grad student ended up on the Colbert Report. He was interviewed by him, right? Became very famous. While the Harvard professors were like, oh, we were right, even though they were definitely not. They got proven wrong. Okay, so let us practice. We have some data in front of us. And so what I would like you to do, you do it on your own, but feel free to turn to your partner and be like, I don't know what's going on right now. Like, how would you do this? Feel free to talk. And with the data here, I want you to do 3 things. Construct a frequency table. In doing so, make sure you calculate proportions and percentages. Then create a histogram for what this data might look like. And then once you've done that, you've kind of drawn it out, what does the shape of that distribution look like? So feel free to start working on this. I'll walk around. I'm very bad at walking around. I just find it the most uncomfortable part of my job. So if I'm creeping, I'm not. I'm just so uncomfortable. I probably feel like I'm creeping. But I'm there, to answer questions. But let's start, kind of practice. Can we answer these questions? If not, talk to your partner and be like, how would you start this? Yeah. I've already done the first half of it by creating this, right? And so frequency table, frequency being like how many, is asking us to kind of just write down our numbers, 6, 7, 8, 9, 10, 11, 12, 13. And the first column is called the frequency. So how many? Frequency. And we know that from our chart that we just made. So 1, 4, 5, 3, 3, 2, 1, 1. Now comes proportion and percent. So I was walking around, I had suggested you didn't necessarily know how to tackle this. You might have like a better like, mental understanding of what a percent is. And so, but either way, to answer what are the proportions, what are the percents, we need to know one more thing about our data that we haven't like, said out loud yet. If I want to know the percent of something, what do I need to know? How many total there are, right? So we need to know like what is the bottom number, right? And so how many observations do we have? How much data is in front of us? 20, right? So our N, we're going to say is our sample is 20. So what is 5? We're going to start with 8. What is 5 divided by 20?
0.25.
0.25. We have calculated our first proportion. Right, so proportion is a number from 0 to 1. It's a fraction. Well, we then translate it into a decimal point, right? So it's proportions from 0 to 1. And if we wanted to change 0.25 to a percent, what percent of our data is in 8? 25%. 25. What you could do is say like, well, I just multiplied the proportion by 100. Or you can say I moved the decimal point over 2 places. Both would get us to percent, which is 25. So with that, we can kind of fill in the rest. What is 1 divided by 20? Yeah. 0.05, 0.05, 0.05. This one is 0.20, and about 3 divided by 20. 0.15. 0.15, 0.10. Now, since I said proportion is a value from 0 to 1, then if we add up all these together, we can double check our work and find out that this all added together should add up to, what do you think? What proportion of our data is a certain number? So if I tell you the proportion of every piece, right, you get 0.05% of my pie, I get 0.25% of my pie. By the time it's all over, 1, right? We get a full pie is given out, or 100% of the data is discussed. And so this is a frequency table. We look at our values and we count up how many times do they occur, and then we can translate that into the proportion or the percent of the data. And you can use any of these 3 to create a histogram. They would look the same. Questions on that? All right. So what do you think? Let's think about, oh gee, erase. Can't read it. While I trip over the wall. We're having some like kind of practice questions regarding distribution. So think about they're kind of, I'm asking, making you think about two different kinds of distributions in this question, a loaded question. So we have heights of student at Stonehill. You can imagine we have differences there. But our distribution of heights here at Stonehill might differ in some way from students at Smith, which is an all-women's college. How might Smith's distribution of height look differently in terms of shapes? Like, what is our shape of height probably like? And theirs probably doesn't have. Sorry, I couldn't tell if that's hair or hand. It was a hand. All right, go for it.
At this college, it would probably be more uniform looking, rather than our school would probably be more.
Okay, why would our school be askew? Tell me about that.
The greater.
Why is ours greater in their differ in their differentiation? Good. So first thing you're pointing out is that we have two different genders here on campus, and that's different than Smith, an all-women's college, right? You are one-upping me on my question by pointing out that women have a smaller range in their distribution, which I think is true for most things. If you look at gender, they tend to be a little bit more compact in their distribution. But so you indeed, right? So you have two groups here at Stonehill, and they have their own kind of like distribution of shape. Yeah. And Smith might have just one because they're all females. That's all correct. But now let's think, okay, on average, is there one gender that is generally taller than the other? Getting some nods, yes. Okay, so what gender would be generally taller? Men, right? Males, right? Great. And so if that's the case, you can imagine there's some distribution of height here on campus where men, range from some number over here to over here, right? This is probably like our basketball team, football guys, definitely not me, right? They're over here. And then we said that women are on average going to be a little bit shorter than them. So they have a distribution, but they too probably vary, right? There's some women that are maybe shorter than you and some that are probably taller than you, and people still have this about an average, right? So you can imagine theirs might look something like this. Yeah. So women are shorter than men on average, but they both have this kind of spread. So let me just edit my drawing a little bit. What kind of distribution does this look like now? Bimodal, right? And we can kind of say a little bit symmetric, right? So it's a bimodal symmetric distribution. So this is Stonehill. You can imagine that there is one group for females that has a certain thing, and one for males, but when we put them together, the height looks like this. And how is that different than Smith? What kind of distribution does Smith have then? Unimodal, great, right? And we can imagine we're probably no different than Smith as far as our heights of our women. I don't know that for sure. So it's probably over here. They just don't have that extra tall group, like the tall men. Now the short men still exist, right? Dr. C, right over here somewhere, because I'm on that side of the curve. Because you don't see that line, I just hang out over there. I still exist, I'm just hidden in the graph. Okay. So what about rolling a six-sided die, what kind of distribution would that be? Uniform, why uniform? Random, tell me more about that, you're right. What does it mean to be random? Like it's a equal chance, right? Like everything has an equal chance to be whatever you roll, right? There's no difference. It's random, right? It's going to be a one, a two, a three, a four, a five, six, equally likely, right? So if it's equally likely, then I mean this would be 1 out of 6 times, or maybe out of 100 rolls. Nope, 1,000. That's fine. That the 1 hits that many times, the 2 hits that many times, the 3 hits that many times, the 4, the 5, and the 6, right? They're all the same height. And if they're all the same height, then we say it's a uniform distribution, right? Very good. What about, I feel like this question actually wasn't the best question, but we're gonna try. Where's my note on it? Commute times in Boston, the greater Boston area. What do we think? What is that going to look like? And so what we can do if we don't know, right? The first thing I would do is just set up a graph and say, how many, right? So how many? And then it's commute time. So I'm guessing this means like 0 minutes. Your office is right outside, or maybe it's from home. To here, I don't know what the longest commute to Boston would be. Maybe someone drives 2 hours to get to work.
Bimodal?
Okay, tell me about that. Mm.
Down.
Ah, good. So you're thinking kind of like across the day, what is that looking like, right? Like if I'm commuting into work at noon, I'm probably not hitting a lot of traffic. Yeah, great. And so this is good because it helps me be like, oh yeah, that's a good way to answer the question, and it means I need to edit my question wording. So very good. I guess I was thinking more like, on average, you ask someone like, how long is your commute in? Like they're gonna say like, oh, it takes me an hour to get to campus, right? Like I say it takes me 50 minutes to get to Stonehill. And so, but that's different, right? Other faculty members are gonna say it takes me 15 minutes to get to Stonehill. So we're thinking about people who work in Boston. When you ask them, how long does it take you to get to work? So like we're trying to not consider the fact that they could be coming in at different times, but it is a good point. And that'd be a very high level question to ask. Yeah. Okay.
So some people might take 15 minutes because they live close. And if there's a lot of time, but people move in from where that's something.
Great. I can see that and I agree. So I guess what I was thinking too, and tell me more about this, like being in the city. Why is it easier for someone in the city to get to work versus being outside the city and having to drive in? Or maybe better stated, how is someone who lives in Boston, working in Boston, different than someone who lives in Easton, working in Easton? What do people in Boston have access to? Transportation, what kind of transportation? Yeah, the T, right? Yeah, and so like that might help speed up their commute if they're in the city, right? But if they're not in the city, then there's going to be a good amount of people over here who take a lot to drive in, right? But you have a good amount of people who are in Boston. I mean, Boston's a big city, and I don't know how you're living in Boston and not actually working in Boston. How can you afford rent then? Fine. So like their commute is probably shorter. I agree. There's probably still a range there, right? It's not like everybody, but because they're probably going to be working in Boston and they live in Boston, that is probably going to be pretty tight. And then we have the commuters, right? And how awful their lives are. And so it goes on. But if you drew it out and you like wrote, maybe you drew 2 peaks and then you explain like, well, I think it's 2 because of the commuters and here's why, like, great. Stats doesn't always have a single correct answer. So you said, both of you said bimodal, you gave good reasons for why. I'm just giving you my perspective on how I was thinking more about positive skew, but I can see both. And what about retirement age? How might it look? So again, we keep that how many, and now I'm asking what age you retire. So we can imagine a 17, 18-year-old can retire all the way up to 100 years old. Could still be working. Okay, tell me about that.
First, with the amount of retired people, and then they'll start to go down a little bit. I don't know.
Kind of dark. I think we're suggesting that they die. And so then they're no longer included in our data set. Yeah, so I mean, but I can see that, right? Like at some point, like here, it's gonna be this tail where no one's probably retiring at 18 unless you just won the lottery or something and you're good, you don't need to work again. And at some point, most people are gonna retire around 65, maybe it's 67 at this point, because everyone doesn't have savings. 67, and then less and less people, like the amount of people left in the workforce is smaller. And so that's why you're suggesting like, all right, well, it's going to go down a little bit because there's less people able to retire. And, but that itself would have a normal distribution as well. Okay, right. So you're saying it's like a second one here until no one, because they're dead. Something like that is kind of what you're imagining in your head. Okay, good. Yeah. If you just said kind of negative skew, you were like, well, something like this, poor negative skew drawing, Dr. C, but that'd be good too. Right? You're just like, well, less and less people are going to be retiring at 100. Yeah, there's not going to be a big jump at 90 where then more people start retiring. Less and less people start retiring as they get older because they already are retired. That'd be good too. Okay. Let's see. So let's say we're interested in talking about the population of different US states. And I've graphs 1, 2, 3, 4, 5, 20 states here in their population. Looking at this data, what do you note about the distribution? Is it unimodal or multimodal? Is it symmetric, positive, or negative? Or is it symmetric left or right? Whatever you would like to say. Yeah. Right skew. Okay. So it goes out towards the right, right? It goes to the positive direction. Good. And is it unimodal or multimodal? How many peaks does it have? Yeah. Unimodal, right? Yeah, there's one peak right over here. Most states have a small population of between 1 and 2 million. And there are some states in our data set that have up to 39 million people. Okay. So here we have our data set. I put it up here for you. Here are 20 states. Now, what I'd like to ask you to do is attempt to calculate the mean, or sorry, the mode, the median, and the mean for this data here.